Thank you. Good afternoon, everyone, and thank you for attending today's webinar on designing masonry for energy efficiency and code compliance with our Wall Systems Research and Development Manager, Leroy Danforth. My name is Brian Yansak, and I am the Design Studio and Events Coordinator for Glen-Gery. During the presentation, you will notice the Q&A function at the bottom of your screen. Please feel free to submit any questions throughout the presentation, and they will be answered at its conclusion. Your attendance will be marked, and we ask that you stay on for the duration of the presentation to receive your credit. Everyone attending the duration of the course will be receiving a certificate of completion within the next few business days, and those who provided their AIA number during registration will be submitted for AIA credit as well. If you are participating but did not register and wish to receive AIA credit, please email events@glengery.com. That is events@glengery.com with your information, and I'll be happy to make that happen for you. Today's session will also be recorded, and a link for you to access it will be provided within your certificate of completion. I would now like to introduce our speaker today, Leroy. Leroy Danforth is a licensed professional engineer who has provided technical guidance to the building community for more than 20 years. Leroy's contributions include a variety of technical articles and publications on brick construction, participation in the development of masonry codes and related standards, and advancing industry knowledge via hundreds of continuing education seminars, just like today's. Leroy's current work focuses on testing, development, and technical support innovation of non-traditional masonry assemblies. Leroy earned a bachelor's degree in architectural engineering from North Carolina Agricultural and Technical State University, and also holds a master's degree in construction engineering from the Catholic University of America. And with that, I would now like to turn it over to you, Leroy.
Thank you, Brian. Are you able to hear me well?
Can hear you and see you.
Okay, great. So I'll run right back to the beginning here. Welcome, everyone. Before we actually get into today's program, just want to take a few minutes to share some things with you about Glen-Gery and our products. If you logged on a few minutes early, you got a chance to see some highlights in the introductory videos. Our company, Glen-Gery, is one of the oldest and largest brick companies in the United States. Glen-Gery was founded in 1890. And our parent company, Brickworks, which is headquartered in Australia, was formed in 1934. So two large and old brick makers. We have manufacturing plants across the Northeast and Midwest that incorporate both brick manufacturing plants, as well as we have a manufacturing stone facility. And we're sold nationally and have a network of over 500 distributors throughout the United States as well as Canada. So just to give you a few notes on some of the products that we're proud of and would like to highlight, make sure that you know about. We are also offering some import specialty products as well. One is our San Selmo line of brick, which is they're a long format brick, which is something that has becoming more and more popular over time. So if you want to take a look at that, this is just an example of one project that features it, a couple of different textures that we have available, and obviously a number of different colors. We offer an imported Venetian glass product, which is offers a great opportunity to add some accent, some interest to your projects. A little bit goes a long way as far as these, but this is another thing that we add to the design palette. Our clay coat brick is a brick with a breathable coating rather than a glaze. The primary benefit of this line, even though we can do them in all colors, is that the very popular cool gray tones that people are looking for, it's usually with a natural clay and natural additions that we add to a brick body, you get the warmer gray tones. But if you're looking for those cool grays, a clay coat is an option. It is, even though it's a coating, it is over a gray body, as you can see in the photo there. as well. And so these are some offerings that are very good for those types of projects. We are one of the very, very few makers still of handmade brick in the United States. I think there's probably only a couple or three left. So if you need a brick that looks 300 years old on a brand new building because of context, then this is one of the options for you. We're very proud of our handmade line, which we make at our York plant. So I showed you the San Selmo brick, which is an imported long format offering. This is a Roman Maximus brick, which is another long format offering, but this one is made here in our plants domestically in the United States. So slightly different colors available. And certainly if you want something that's made here in the US, then this is an option for you in that regard. Creative Minds, we are a distributor for. This is a very high quality manufactured stone product with some really detailed textures, as you can see here on the slide. So we're proud to offer that. And then we do have our own line of stone that we make in Cynthiana, Kentucky at our plant there. And that is the Landmark option. So two options as far as stone is concerned. We still do make pavers as well. We are a manufacturer of clay pavers, so we have a number of options available there. Feldhaus is another one of our import options. They focus primarily for us is in thin brick, particularly thin brick that have really tight tolerances for things like precast applications. This is something that greatly expands the offering that even we can make from our lines in our plants. So the Feldhaus is an option there. In addition to our brick products that I've just shared with you, some of those, we also have two systems for thin brick. So these are systems where the actual panel or rail that holds them is a Glen-Gery product. And so from that standpoint, we're able to offer you a full wall system assembly. The one you see on the screen here is a True Bricks assembly, which is a rail product. And so it uses special brick that are grooved top and bottom, gives you a really nice, secure mechanical interlock between the brick and the rail system. We also have our ThinTech product, which is a panel system. So that one uses little punches on the panel that support the brick and also give you they act as a tie to give you a mechanical engagement through the mortar joint. So two options, some work better for some, one may work better for some applications than others, but we do have two options depending on what works best for your project there. We also are able to help with accessories, the things that happen behind the wall assembly. So all of the materials that you see listed here, from rigid insulation and wall ties to things like weed vents, mortar collectors, and air and water barriers. We are able to assist with those, help you with specifications, with reviews of plans, details, all those kinds of things. It's one of the things that we're very proud of is that we're not able only to offer you products, but we're very proud of the support that we can provide along with those products as well. And this is just a look. We have a whole team of really specialists. I look at this team, we've got ceramic engineers, architectural engineers, we've got thin brick product specialists, we've got masonry estimators, we've got shapes people, we've got stone people, a little bit of everything represented here. And so please don't hesitate to reach out to us if you have questions, and we'll do our best. And here's a look at our values, our Brickworks values. We care. We try to be sustainably safe in everything. We innovate. We try to, everyone, everywhere, every day for continual improvement to come up with the next thing. We collaborate with you so that we can succeed together. In terms of integrity, we try and do what we say that we're going to do. and through all those things to lead, to inspire all of those that we work in conjunction with, to play passionately and win and exceed every expectation that you have. So thank you for joining us today. And it's time for us to get into our program. So our topic today is energy efficiency and code compliance. Our program is approved with AIA for 1 hour continuing education credit. I'll just remind you one last time, if you didn't RSVP, make sure that we get your information after the program so that we can properly record your credit or send you a certificate. So to take a quick look at what we'll discuss today, the material that we'll cover, we'll talk about changes in the building code related to energy efficiency and fire safety. And as these things are changing, what their impact is on the way that we construct and design and detail masonry wall assemblies. So we will cover some energy efficiency strategies. We'll talk about compliance paths, and we'll talk a lot about insulation, because typically when we have a conversation about energy efficiency, that's one of the things that's going to come up. As far as actual learning objectives, you can see here that we will review the background of the current energy code requirements. We'll talk about how continuous insulation affects both anchored and adhered masonry veneer. We will identify some requirements that are related to the use of combustible materials and non-combustible wall assemblies. And I will try to share with you some design strategies to help you get the most or reduce energy use the most through the design of your masonry wall assemblies. So this is just a little bit of an introduction here. We can see you can find statistics like this just about everywhere, and the numbers may change slightly from source to source, but the takeaway is that our buildings, and particularly commercial buildings, consume a lot of the energy here in the United States and the lion's share of the electricity. Um, U.S. buildings, commercial buildings, are the largest source of global warming pollution, and they emit quite a bit of our total greenhouse gases. So it's certainly a sector that we have to pay attention to. And that's why, of course, our building industry has been trending towards doing everything that we can to reduce energy use and make our buildings more sustainable or high performing. One of the things that I would like to do today is have us to change our thinking just a little bit. When we think about energy efficiency, we usually don't think of it in the same context as we think of our energy resources, things like wind, water, electricity, all those. We sort of put energy efficiency in a different bucket. But if we were to consider it as a tangible thing, like those other energy resources, what you'll find is that energy efficiency, or being energy efficient, is very often cheaper or faster or cleaner, and sometimes all three, than those energy resources that we have available to us. And what that tells us is we definitely need to pay attention, not just to the supply side of the equation, but the demand side as well. And most of you, being problem solvers in the building industry, we realize that very often the best solution to a problem is not just one thing; it's a combination of different strategies, and that's certainly true here. Even though we can put those PV cells and those turbines and all those kinds of things on our building to help us, we get much farther if we also tackle the demand side of the equation as well. So this is what the Energy Information Agency, if you take a look, they do a building energy consumption survey continually. And I just chose 2010 because it most clearly tells a story that I'm about to share with you right now. If you look at other years, the numbers will be slightly different, but effectively the same. So if you take a look at the way that commercial buildings use their energy, if you look at the chart here, you can see very quickly and easily that just about half of the energy that's used by commercial buildings goes into HVAC and lighting. And depending on the numbers that you look at from year to year, this one's a little bit off, but usually the HVAC is about a quarter of the total energy, and the lighting is about a quarter of or about a quarter of the total energy. So you can see that reflected here. The numbers are off a little bit from that, but still in the same ballpark. It makes it very easy to see that if our discussion today is about reducing energy use, that if we try to tackle the big pieces of the pie first, then that's where we have probably some big opportunities to make a change. So if we begin to look at strategies, so lighting, we saw in the previous slide that lighting is about 20%. As I said, depending on the building type, the building use, it could be more than that. 25% would not be unusual, in some buildings even more. So the reason lighting is shown at the bottom of this particular uh, diagram here or illustration is it represents a low-hanging fruit. No matter what type of building we're designing or what its use is, we have a number of different strategies available to us to reduce the lighting load, whether it's daylighting, spot lighting, motion controls, those kinds of things. They are usually not very expensive technologies, and they can be applied in a variety of ways to reduce our lighting load very easily. And so that kind of represents the low-hanging fruit. We mentioned the HVAC portion being another large chunk, but in this case, you can see it's higher up on the chart. And that's not because the opportunity is not there. It's just simply because the flexibility may not be there, depending on the type of building that we're building and what its use is. Of course, we have minimum limits for performance of all of this equipment. And because it is mechanical equipment, there's also a maximum efficiency that we can get out of it. So we're dealing sort of in a narrower band. And then, as the performance increases, there's a bit more usually of a performance premium from the standpoint of cost as we get equipment that works better or is more efficient. And so it's certainly an area for us to look at. Lots of opportunity and potential there, maybe just not quite as easy as an area like lighting. And then in the middle of the chart here, you can see some other things mentioned like building commissioning, making repairs and adjustments based on actual operating conditions. Those are fairly easy and can have a big impact. And then looking at the way that we actually design the building envelope itself. And that's where we're going to spend most of our time today, is in that area. So here's a look at a couple of categories that we saw on the previous slide. And even though everything is broken out into nice defined categories here, it makes sense for us to acknowledge that in the real world, it doesn't happen like that. There's some interplay between these categories as well. But this is an example that's getting fairly old now, but it still makes a good point. So we have two wall assemblies here that we're comparing. Wall A with an R value that you can see is not very good. Let me tell you that is an effective R value, not what you would get if you were to add up the component resistances to the wall, but how this wall actually performs. And what this represents is basically any metal stud wall, 6-inch metal studs, R19, R20, R21 bad insulation between the studs, but no continuous insulation. You don't have continuous insulation in that wall assembly. This is about the performance that you can expect because of the thermal bridging through the studs. There's also a window shown here. This would represent something that has no special coatings, no gas fill between the panes or anything like that, just pretty standard glass. You can see our winter and summer design conditions. You can see how much envelope we're looking at there. So we're looking at, roughly 30%, 1/3 window to wall ratio. And you can see the actual HVAC load coming through each of these materials here, your opaque wall and your window. So a total of 20 tons through the wall, 35 through the window. Remember, the window is only about a third of your area, but it represents the majority of the heat transmission. And so higher load due to that. And then a total of about 55 tons. By comparison, wall B here, you can see has an effective R value of R20. We can take that same metal stud wall assembly, and we can see that the difference here is roughly R13. So if we choose a common material like extruded polystyrene insulation, it has an R value of about 5 per inch. So if we had 2.5 inches, that's about R12.5, which is just about makes up the difference between these two walls. We'd be at 19.5 rather than R20, but effectively the same. So if we make that one change one material in the assembly, look at the impact. We go from an HVAC load of about 20 tons down to about 7 tons. So we reduce reduce the HVAC load through the opaque wall by about 2/3 just by making that one change. Very simple. Also, if you take a look at the window, if we can get a window that performs better, transmits about half as much heat as a previous one, then obviously that's going to cut the thermal transmission by half. And overall, you can see the impact there. So these are very simple changes, very simple things. If we take a look, just looking at the HVAC component, for example, if that represented 30% on the previous slide of our total energy use, and we can cut it in half, making changes just like these two, very simple changes, that represents 15% of the total energy that building uses. So that's significant and definitely the kind of thing that we should be considering. So when we look at our requirements or our criteria, they come primarily from two places. The code being the International Building Code, as well as the International Energy Conservation Code, and then standards, which may not be mandatory, but they do provide some good guidance, and sometimes they are codified, sometimes they are made mandatory. So these, the two that you see on the screen are the two that people are most familiar with and most often govern in the areas where we live. Current version of the ICC is 2018. Current version of ASHRAE 90.1 is 2019. So in terms of these energy requirements and how do we figure out, okay, how does our building actually need to perform when it comes to energy? It's basically determined by the climate zone that you're in, the type of element that you're designing, and you may have some options when it comes to compliance paths. So if we take a look at each one of these elements, first thing is the climate zone. And on the slide here, you can see the International Energy Conservation Code map and the ASHRAE map side by side. So you can see they use different descriptive terms, they use different colors, but if you look at how the areas are actually laid out, how they're defined, you can see that the map is effectively the same map or very, very similar in terms of how the zones are. So what that tells us basically is that, the climate itself is the same from map to map. It's simply what we do about that climate that changes. So the ICC and ASHRAE 90.1, they do have different requirements, or they can be different from time to time. Here's the simple explanation for that. When we look at the energy code, code is always minimum requirements for something. The ASHRAE standard, on the other hand, ASHRAE is a trade association. Trade associations typically promote best practice. Okay, so there's always going to be some room or a gap between minimum requirements and best practices. And so that's why when you compare the two documents, very often you'll see that the ASHRAE 90.1 standard is actually more stringent. It's more restrictive than the Energy Conservation Code. There are times when the code catches up and they're on the, they have basically identical requirements, but usually ASHRAE leads. So if you ever want to know what's upcoming, maybe in the next version of the Energy Conservation Code, you can look at what's in ASHRAE 90.1. And if it's different, it's a pretty good indicator of what may be on the horizon in the code. So at this point, we also have different compliance paths. But these criteria change over time. And for metal frame walls, which we'll use as the example today because it's very common and it represents the worst case scenario for most of us because of the thermal bridging. Here's a look at what the requirements are in the code that most of you are on, the version that most of you are on. If you're on 15 or 18, in most cases, this is what it's going to be your minimum R value requirements for prescriptive insulation, which means if we're doing a metal back wall, you have to have continuous insulation in the assembly. And that has had some pretty significant changes on the way that we build things like masonry veneers in these wall assemblies. So to talk a little bit about the different compliance paths, you have prescriptive, which is the R value or U value tables are a very good example of those. The benefit of a prescriptive method of compliance is that it's simple, okay? You don't have to know a lot. You can look at a table, it has criteria for you. You can maybe pick a wall assembly or pick assembly components directly from the data that's available from the manufacturers without having to have a building science degree. So the trade-off of that simplicity is that there's not as much flexibility there because there's a requirement or a criteria for basically every element. So as we move along the continuum towards a performance-based approach, we have things that introduce trade-offs and some basic software, spreadsheet type software can actually introduce those trade-offs. If you're familiar with ComCheck or ResCheck, those are good examples. They're able to take the elements that we choose and determine on a system basis rather than individual element basis whether we're going to meet certain benchmarks for performance. So that gives us a little bit more flexibility while adding some complexity, making it difficult to do things like hand calculations, for example. Then at the other end, we have things like whole building analysis. These are going to be your modeling softwares, your energy simulations, annual energy cost budget, that kind of stuff. It takes complex software to, account for all the moving parts, to account for, solar cycles, dynamic. So what I'm looking for. The effects of time, and changes in temperature, and so on. But the big benefit of doing these or using the modeling for a masonry assembly is that the modeling has the ability to model thermal mass or the effects of thermal mass. And you're going to lose that when it comes to your prescriptive and your trade-off based methods. So if you take a look here, you can see that there is in the prescriptive table a line item for mass. However, that line item specifically excludes things like a standard brick veneer, 4-inch brick veneer. And that's why the industry has been working to quantify the actual thermal performance of brick veneer. If you look at the requirements in ASHRAE 90.1 or in the IECC, for what's considered mass. It comes down usually to a heat capacity or a weight. And in both cases, a brick veneer will meet the criteria for either the heat capacity or the weight. But the reason why they're excluded is because initially we were unsure about the impact of that mass when it's sitting on the other side of continuous insulation, because there was concern that it negated or significantly reduced the effects. So the National Grid Research Center at Clemson University has actually been doing some research to take a look. And again, we've got steel stud walls as an example, as well as CMU wall. But they did different wall assemblies. You can see down in the legend here at the bottom. Brick veneer walls with extruded polystyrene insulation, 2 inches. EIFS walls over the same steel stud backup wall, or CMU. And then the reference wall assembly, which is the steel studs or the CMU as you see here, with no cladding, but with the 2 inches of extruded polystyrene, just like the one with brick veneer. And so what you're seeing here are the results. This is total heat transfer through the wall per day. So in this case, big numbers are bad. We want less heat going through the wall, transferring through the wall. So if we take a look at the brick, steel stud backing wall with bad insulation, brick veneer, 2 inches of extruded polystyrene. You can see that there's going to be about 15 BTUs per square foot per day of heat transferred through that wall. Look at the EIFS wall, 26.4, okay? And then take a look at the reference wall, the steel stud with the bad insulation, 2 inches of XPS, but no cladding at all. It actually performs better than the EIFS wall. Okay, now that definitely seems counterintuitive to a lot of us, a lot of you, including myself. So I need to explain these numbers. So the first thing that we'll look at is these two. Why, if, obviously EIFS is continuous insulation. So why would an EIFS wall allow more heat to flow through than a wall with 2 inches of continuous insulation and no cladding? And the reason for that is the EIFS that was used here, it was with 2 inches of EPS insulation. But XPS has a slightly better R value per inch than EPS does. And so that is what explains the slight difference. Obviously they're the same ballpark, but why the wall without the cladding, without any cladding in XPS actually works better than an EIFS wall. The EIFS has a little bit of weight to it, but not enough to really make a difference. The big difference that you see between the brick veneer wall, which has 2 inches of XPS, and the EIFS wall, which has 2 inches of EPS, basically this difference, this gap, is explained by the weight, the thermal lag, the thermal heat capacity of the brick. So you can see that this trend follows if you take the bad insulation out of the steel stud wall and use only continuous insulation. And in that case, the gap gets even larger, from 20 to basically 40. And if you have a CMU wall, which would introduce more mass into all these assemblies, so they all perform better, but you can still see basically the same trend holds here. So here's another chart, another result or output from that research. And in this case, we're looking at the number of hours until the peak energy usage. So to explain this and why this is important, the number, when we think about R value is a number that's steady state. I know that we've all heard that before. And so it doesn't take into account the actual heat capacity or the ability to thermal storage in a mass material. So when you think about heat flowing through a wall assembly, if we look at the R value for brick, for example, And we say, oh, well, the R value for brick, it's very low. It's really bad. That's true. But that number is not reached until the total heat storage capacity of the brick is all consumed, at which point heat can flow freely through. So what this chart gives us is an idea of how long it actually takes before that peak heat flow, before that steady state condition is reached. So again, you can see the same wall assembly, CMU, steel stud with and without bad insulation. And we see the same trends as before. Let's take a look at steel stud with bad insulation. So in this case, it's about a 6-hour time lag from when heat is first applied to the exterior of that wall assembly to when it actually reaches peak energy usage, or in other words, the highest heat flow through that wall assembly. So about a 6-hour time lag. By comparison, take a look at the reference wall, just the steel stud wall with no cladding, at just under 3 hours, and the eaves wall, which is just over 3 hours. So basically what this is telling us is that the contribution, the additional heat storage capacity of the brick is about an additional, almost an additional 3 hours. And so during that time, the R value of that brick is not what, our steady state numbers tell us. It is approaching that number, but it begins at 0 until it approaches that number about 6 hours later. So because of this research, the industry is actually trying to present this information to the code body so that when you design with masonry claddings, you can design with these numbers being quantified and it making it easier for you to design your masonry assemblies and meet the energy code. Basically, this will mean that you will be required, just like in the mass line that's currently existing, you won't have to use as much insulation, or your transmission value that you can use will be slightly different if you're using these materials. So the next thing that we should consider if we're trying to reduce energy efficiency, to improve energy efficiency and reduce energy usage, is to go a little bit further with thermal bridging. In a brick masonry assembly, if we're talking about commercial construction and it's, multi-story, anything over 3 stories, we're probably going to have shelf angles, and those shelf angles are a thermal bridge. So we've got 3 examples here: steel stud backup wall with a shelf angle that is, continuously attached to at the floor. We've got a poured concrete backup, again, continuous attachment of the shelf angle at the floor, but with some continuous insulation here, and then exposed slab edge. Exposed slab edge, obviously that's going to interrupt your insulation. Basically this becomes a heat exchanger. And if you're like me, you've seen many, many articles and presentations which tell us that this is the absolute worst thing that we can do. Some of you have seen infrared photographs, thermographs like these, and can decipher them. But basically, when you take a look at something like this, and when you actually do the hot box experiments on these types of wall assemblies, what you find is that this, where your layers, your colors kind of stay in place, that tells you that you don't have as much heat flowing through as when you get something like this. You can see there's more of a difference. You don't have those bands of the color that kind of stay in their places. So in both of these cases, and just think about this intuitively, what conducts more heat, concrete or steel? Steel does. So we can see between these two, obviously the continuous insulation, it helps. But when you look at the actual numbers, you can find that a detail like this may actually be worse than a detail like this with the exposed slab edge. Now, with that said, I'm not trying to convince anyone that this is a good thing, it's still not great. 46.4% reduction in the R value of this assembly, that's not where we want to be. And that's the reason why our industry is moving more towards these types of connections for the shell family, where rather than being a continuous connection, you have intermittent connections with proprietary hangers or tube steel or clips or something of that nature. And so because of that, you have much less area for that heat to pass um, continuously through. It also gives us an opportunity to incorporate the continuous insulation, which further improves the performance. So rather than on the previous slide, when we're looking at a reduction in thermal efficiency, basically on the order of about 50% or half, now we're looking in the range that's more like 15, 16%, and that's much, much better. Some other things that have come out of recent research that you may find helpful is if you're familiar with radiant barriers, all of our masonry wall assemblies have an airspace in them, or they should. So anytime you put a reflective surface on one side of an airspace, it actually improves the thermal performance of that airspace. So again, through some hot box experimentation, we were able to quantify this down at NVRC. This actually shows numbers from the residential study. However, when they did the commercial wall assembly, the same trends were reflected. But the wall was an R14.5 wall that was the calculated R value of the assembly when they used a pretty standard water resistant barrier. They made one change in the wall assembly, which was instead of using that, pretty standard air water barrier, they changed it to this reflective material, or to a reflective material, perforated to allow vapor to go through. And they saw that the calculated R value for that wall went from 14.5 to 17. That's measured performance. So just by making that one change, that's almost a 20% increase in the thermal efficiency of that wall assembly. So pretty significant when you consider how small of a change that is. So if you have an opportunity to use something like a foil-faced insulation in your assembly, something like that, it could have some pretty significant benefits. Not applicable to every project, every assembly, but where we can employ these things, they are certainly helpful. So to go just a little bit further on the impacts of these changes to the building code, and specifically increasing requirements for continuous insulation, probably the most common ones that we see used in masonry assemblies are going to be the ones on the right side of the screen. Spray foam is also used in some cases, but you see a lot of foam insulation that's represented here, which was sort of the material of choice until relatively recently. And if you're not aware of the reason why more and more we're trending toward mineral fiber as an insulation, the primary reason is because of the impacts of fire. Most of these assemblies that we're talking about using steel studs, they are non-combustible wall assemblies. However, foam insulation is a combustible material. And so when we couple these, foam insulation into these non-combustible wall assemblies, we realized at some point that meant that there was something in the code that required us to have special testing and an FPA 285 approval. The mineral wool, not being a foam insulation, does not have to have this approval or have this test done. So just a little bit of background on this test for those of you who may not be intimately familiar with it. It's a 2-story wall assembly burn test, and it simulates a fire that begins within or on the interior of the building and then flashes over, makes its way to a window and out the window. So if we take a look, this is sort of how the test rig looks, where this is a big wall panel. This is the furnace or the burner. It's 2 stories. So there's a burner in here on the first floor. So they turn that on, they wait 5 minutes, and then they turn on another burner at the simulated window. And that represents the flashover of the fire. So when everything ignites and it busts out the window, and flames come out there. So really what we're trying to determine with this test is what is the likelihood that if fire makes it to a window, that it's going to make it, laterally out to another window or climb up the facade to the next floor and make it to the window so that it can continue to propagate that fire. So some of the criteria for the test, some of the things that they look at are, flame spread to either side of the window opening as well as above the window opening. They take a look at flames within the stud cavity. Any flames out of the perimeter of the test assembly. And then they also look, they have thermocouples. They are looking at the temperature within the wall as well. And Brian, I just want to check, I see a comment. Are you able to hear me?
Yes, I can hear you. I only saw one person commenting on that.
Okay. All right, so I'll continue. So this is a look at 2 different wall assemblies and how they perform in the test. Same backing wall assembly. In this case, on the left, you can see is a non-combustible cladding. It's masonry. On the right is an insulated metal panel. So looking at that 10-foot criteria, you can see the marks because this is a light color. And you can see obviously that goes above the 10 feet there. So that would be a fail. There are a number of things that may trigger this test. As we saw in the previous slide, there are some cladding materials that because of the cladding material, if it's combustible, you may need to do the test. This is an assembly specific test, like a lot of our fire tests. The way that the assembly is tested is the only thing that documentation applies to. You may look at some NFPA 285 test results and say, hey, that's very similar to the wall that I want to design. But if you change the water resistant barrier that's used, if you change the insulation manufacturer, if you change the insulation from 2 inches to 3 inches, at that point, you need new documentation because all of these things have an impact on the performance. So even though, XPS, EPS, polyiso, spray foam, they're all foam plastics, they all perform differently in the test. So again, assembly specific as far as those, as far as your air and water barriers. If you want to take a look at where this material is in the code, the requirement in regard to foam plastics or foam insulation is in chapter 26. As far as different types of claddings, you can find that in chapter 14 of the code. If there's fiber reinforced plastics, that's back in chapter 26 as well with the rest of the plastics. There are some exceptions to the rules. There are some ways that you can build with foam insulation and they are exempt from the test. But you basically have to either cover the foam on both sides with concrete or masonry, or you can have an airspace up to 1 inch as long as the flame spread of the insulation is not more than 25. So there are some exceptions in there, just like with any other rule. So to start to kind of wrap things up a little bit, what I'm trying to present to you today not only is just a background of where these energy requirements come from, but also what sort of impacts they have. One of the big takeaways that I want you to have from this is that, if our building code changes or our energy code changes or, any of these things, we have to consider the impact that it has on the other performance aspects. In one case, in requiring more continuous insulation is a great thing from an energy standpoint, but it had a very significant impact from a fire performance standpoint because of the types of insulation that we were using to meet these requirements. This may carry over into structural capacity. It may carry over into things like water penetration resistance, air leakage, all these areas. And so what we need to do is to make sure that when we change anything in our wall assemblies, that we think about it from a systems or a holistic standpoint in design. So just a couple of examples here. When we incorporated or began to incorporate more continuous insulation into our masonry wall assemblies, it also had a significant impact on how they behave structurally and what our ties, our masonry anchors were now being asked to do. Uh, so certainly there are ways that we've dealt with this, but just to take a look at a couple of the impacts, we now have to make sure that our masonry ties can help us to prevent water and air infiltration at those penetrations that they make. And so you see that, gaskets and seals on the anchors, or that can be applied at the penetration locations in the form of pressure seal tapes or things like that have come about. And then because of that insulation, our ties are also required to span longer distances. That increased span makes it easier for wind load to buckle that tie. Um, and so we've had to strengthen our ties, reconfigure them the way that they were made in order to make sure they're stiff enough to transfer the load properly. So there was a minimum already in the code. This is just one of the impacts that was 4.5 inches, which was the maximum distance from the back of your veneer to the front of your backing. So if you're still following the 2015 code, that is the prescriptive maximum that your tie can span before you have to have an engineering analysis for that tie. As of the 2016 Masonry Code, and because of the changes that all the tie manufacturers have made to increase stiffness, you can now go up to 6 5/8 inches in the 2018 code with ties that are configured a certain way. This is just one example. You can see here it's a 2-piece adjustable tie. The adjustable piece that goes into the masonry can only span 2 inches, okay? And that's because the backing part, the non-adjustable part, can be made of much thicker, much stiffer material, which carries more of the load. So in this case, if we can limit this to 2 inches, we can go up to 6 5/8. And so that gives us the ability to incorporate, basically an additional 2 inches of continuous insulation in light of energy requirements that tend to continually increase. So here's another thing that can be helpful. There are thermal break ties that are available. So you see another couple of infrared thermographs over on the right side. You can see a standard anchor and a thermal anchor. Obviously, again, those isotherms, they stay in place with the thermal anchor. That tells you that the heat is not leaking or being transferred. One note about this, these are great materials, but if you haven't addressed the thermal bridges at your studs, the thermal bridges at your shelf angles, the benefit of going to a thermal anchor is going to be minimal because those other areas are an order of magnitude greater than the impact of the amount of heat that flows through your ties and anchors. A way to illustrate that, most of us have actually seen an elevation of a building and the infrared picture, and you can see where the studs are. Think about that. You cannot see in those pictures little dots where the individual ties are. And so that tells you that the impact of the studs is much greater than the individual ties. So these are good. They're great if you want to use them, but make sure if you're going to this length that you take care of the big rocks first, and you're looking at things like the parapet details and your shelf angle details. So one final note, the way that the thermal ties work, the way that we reduce heat flow through them, usually the thermal break is in the form of a plastic component. And, you know, we mentioned the NFPA 285 test before. And if we take a look at something like this, if we were to subject this to a fire, that plastic is probably going to burn away. And this is just an illustration of why assembly specific is a very important concept when it comes to these fire tests. At one point, I don't know if it's still true, but at one point I know that there were two manufacturers making two versions of a tie like this. In one case, this entire component was plastic. In the other case, the other manufacturer, this wing was metal, and it had plastic, it was plastic coated, so it had plastic over the top of the metal. So if you think about a test like NFPA 285, we're trying to determine whether, you know, fire is going to, you know, propagate, you know, how much it's going to spread. When you've got 4 inches of foam insulation in that wall assembly, the impact of having this little bit of additional plastic in the wall assembly is probably going to be negligible. It's not going to impact the results of your NFPA 285 test from the standpoint of fire propagation. But in the real world, if this component is entirely plastic and you have a fire, then you just lost the connection between your brick veneer and your structure in that area. However, very similar tie performs the same function, performs the same from an energy standpoint. If this is metal but plastic coated, you've now retained your anchorage between your masonry veneer and your building. And so understanding what assembly specific means, but also that with these different tests, understanding what each of these tests is trying to measure, it's very important. And so that goes back to us, again, thinking holistically about what we're doing and the impacts on different areas of performance. So one final note here, because increasing the amount of continuous insulation typically will make our walls thicker, I believe that's one of the reasons why we've been trending toward more thin veneers. If I can reduce my veneer to 1 inch, then if I need 3 inches of continuous insulation, I can do that without changing the overall thickness of my wall assembly from, you know, a 4-inch face grip. This has some impacts on the way that adhere veneers are constructed as well, because you're now cantilevering that thin veneer, which can weigh up to 15 pounds a square foot, you know, 2 or 3 or possibly even 4 inches away from the wall. And so we have to make sure that the anchors that we're using for those are appropriate. And generally, the manufacturers have proprietary tables for that. But the code also gives us some guidance when it comes to those, so we can have an idea as well. So this is just an example of one of those tables from the code. So in this case, if you've got steel frame studs at 16 inches on center, you can see that if we use a number 10 fastener into an 18 gauge stud or better, that these are the spacings that we would need to use. So we use a 6 or 8 inch spacing along that stud for a number 10 screw into, then we can actually accommodate up to 4 inches of insulation that weighs up to 11 pounds a square foot. So there is some guidance out there for us. So with that, I'll wrap things up. Again, just a reminder that change is inevitable. And so our requirements for building are going to continually change. For you, it's an opportunity as well as a challenge. The challenge is that you have so many products, so many different systems that you're trying to design that you can't know everything about each of them. The opportunity is that through Glen-Gery, through your masonry suppliers, we're able to support you. We eat, breathe, sleep masonry all day, every day. And so when these changes come about, we're among the first to know, how they're going to impact your design. Reach out to us. Don't be afraid to give us a call, shoot us an email. Let us be your resources so that we can make you aware and help you figure out how to adjust for these different changes and what impacts they have on different areas of performance. So with that, that's all the information that I had to share with you today. I believe that there have been some questions that have come in as I've been talking. So Brian, I'm ready to address some questions. That's the end of our AIA Continuing Education System program.
Okay, perfect. We have one come in on envelope performance versus HVAC efficiency. How is BTU values are calculated? Also, window to wall ratio is 0.5.
Okay. So the BTU values there would have been calculated using, just a normal calculation. Trying to think how to describe it. I'm sorry, I'm not sure how to describe it simply. What the calculation would be, but there's a standard calculation that's used in in determining the amount of heat flow through an opaque wall or through a window, and it's based on the amount of temperature change, what your design conditions are, what your thermal resistance is through the assembly, and so you take a look at those things.
Is there a formula to calculate the BTU, if that is easy to explain?
Yes, so there is a formula for it. One of the places that you can find that, the Brick Industry Association has some technical notes on heat transmission in brick. It's the 4 series of their technical notes. The Brick Industry Association's website is www.gobrick.com. And if you take a look there, it actually tells you how you can calculate in the 4 series of the technical notes. Shows you the calculation, shows you some typical R values for brick and different materials, different types of wall assemblies there. And to your point, I acknowledge your point about the window to wall ratio being about 50% in that case. I was thinking I guess I stated it poorly. The window would be about 33% of the total envelope area in that case. But yes, if you were doing window to opaque wall ratio rather than window to overall, envelope ratio, yes, it would be about 50.
Okay, it looks like that's the end. Yeah, it looks like that's the end of all of our questions today. Thank you everybody for joining us. Just a reminder, if you stayed on for the duration of the course, you will be receiving a certificate of completion with a link to the recording of today's session within the next few business days. We would also like to remind you to tune into our next webinar, Beyond the Brick, Masonry Wall Assemblies to Optimize Performance. It's on Wednesday, April 21st at the same time as today, and you will have the pleasure of listening to Leroy Danforth present once again. And with that, I would like to close out the session. Thank you, everybody.